Okay, so since we have a lot to cover tonight, I think we're going to get started. My name is Mary Beth Martello. I am the Town of Wellesley's Sustainability Director, and I'm happy to welcome you to Clean Heating and Cooling for Your Home. We are really excited to see, we had a very high interest in this program. I'm really happy to see so many people here with us tonight. We have a great lineup of speakers, and they are going to introduce themselves before they give their piece of the presentation. And so why are we here? There's many reasons that you may have jumped onto this webinar. Perhaps you have an aging heating or cooling system. Maybe you are thinking about saving on your utility bills, or you've heard about the many incentives that have come online for energy improvements in your home. Maybe you're planning an addition to your house or a renovation, or you don't have air conditioning and you'd like to add it. Maybe you have heard about the studies that are showing that the combustion of fossil fuels in our homes is actually having negative impacts on the air quality and on human health. So as well, perhaps you are worried about the impacts of climate change that we are increasingly seeing in our everyday lives, and you'd like to do something to reduce your carbon footprint. And maybe some of you are interested in increasing your property value. So if you have interest in any of the above, you're in the right place. And heat pumps are a really key technology for what we call decarbonizing our building stock. And so that's transitioning our buildings and our homes to off of fossil fuel. And the three basic steps to decarbonization are: first, weatherize, so insulate and air seal so your home can optimize its efficiency. The second is to electrify our appliances and systems, and that includes our heating systems, and then shifting to renewable energy so we can power this electric need with renewable sources. So those are the three steps. Next slide, please. And interestingly, heat pump adoption rates are rising locally. You can see here a slide showing the residential heat pumps installations in recent years in Wellesley. And you'll notice they're steadily increasing. We had a big jump between 2021 and 2022 with the addition of heat pumps in multifamily buildings. So you see that big jump recently. And nationally, we see a similar trend where in recent years, heat pump sales have actually outpaced gas furnace sales. I also like to point out that our municipality is in the heat pump game. So our new net zero ready elementary schools, Hardy and Honeywell, are heating and cooling with heat pumps, as will be our historic town hall that's undergoing renovation right now, and plans for renovating our Warren Recreation Building also include heat pumps. So you're in good company if you are thinking about heat pump transition. And now I'm going to hand it over to Lisa Wolf to talk about why heat pumps.
I did the classic, forgot to unmute myself. I'm Lisa Wolf. I'm the Wellesley Municipal Light Plant Sustainability Coordinator. And my job there is primarily to help the MLP, help Wellesley meet its decarbonization or greenhouse gas reduction goals. The light plant has a central role to play in helping the town decarbonize because the pathway for the town to decarbonize, as Mary Beth mentioned, is to fully electrify all fossil fuel end uses, including heating and transportation, which is expected to actually double the electric demand in town. So the light plant is making plans now and gearing up for a potential doubling of demand. But at the same time, the light plant is working to eliminate fossil fuels from our electric supply. We're currently at about 70% carbon-free and aiming to get to 100% carbon-free by 2050. So I'm going to talk to you about why heat pumps are so important for reducing greenhouse gas emissions in town. Starting with what a heat pump is and what it is not. A heat pump, first of all, is not electric resistance heating, sometimes called baseboard heating, although it's often confused with baseboard heating because they both use electricity to produce heat. A heat pump also is not producing heat through combustion the way a boiler or a furnace is doing. But rather what it is doing is moving heat from one place to another, which, by the way, is not a new technology. Heat pumps have been around for a long time in the form of refrigerators and dehumidifiers and air conditioners. These are all forms of heat pumps that move heat from one place to another. But what is new is the ability of heat pumps to produce heat for your home using outdoor air, which can even be at sub-zero temperatures. A heat pump now is more efficient than ever before at being able to produce heat for your home, even in cold New England winters. So during the heating season, the heat pump moves heat from the cold outside air into your home to heat your home. And even sub-zero air contains some thermal energy, which can be extracted with a heat pump. But significantly, heat pumps can also work in the opposite direction. So during the cooling season, heat pumps can move heat from your house to the outdoors, much the same way that a refrigerator works. Heat pumps can also be used for water heating, clothes drying, pool heating. The combination of those different forms of heating actually represent about 80% of the total energy use in our homes. So heat pumps can make a significant contribution to lowering our energy use. And what makes a heat pump so efficient is that it can generate 3 to 4 units of thermal energy from 1 unit of electrical energy input. So that means we're basically getting free energy from the ambient air outdoors, and just providing 1 unit of electricity to run the condensers and the heat exchangers and the pumps that distribute the air through your home. So I want to make the point that that's, if you're talking in terms of efficiency, that's a 300 to 400% efficiency compared to a typical fossil fuel system. Even the most efficient fossil fuel systems are just 98% efficient, so less than 100% as compared with 300 to 400% efficient for a heat pump. There are many benefits of a heat pump. First of all, lower operating costs and much lower greenhouse gas emissions resulting from a heat pump. Heat pumps also eliminate combustion byproducts like carbon monoxide or fine particles or soot that may get into your house from combustion systems. And the elimination of carbon monoxide from the home and also the high pressure gas systems can avoid the actually fairly low risk of explosion, but still a real risk, especially if you live in North Andover, you might be aware of that. But also heat pumps provide reduced temperature swings, especially during the heating season, so that can produce more comfort in the home. So what you're looking at in this graph is the horizontal line across the middle. That's the set temperature that you are setting your home temperature thermostat at. And then the temperature fluctuations produced by 2 different heating systems are shown, one in the gold boxy curve and the other in the smaller wavy curve. So a fossil fuel heating system generally is either on or off. So it's either producing heat at full blast or it's off, waiting for the house to catch up. And so that results in these temperature swings that you can see in this graph. But a heat pump, what makes it so efficient is it can run at variable speeds. So you can make small adjustments to the heating and cooling around the set temperature without having these wide temperature swings. heat pumps are also the most cost-effective choice for heating in Wellesley. So what you're looking at is a cost estimate for 6 different forms of heating: baseboard electric, propane, fuel oil, natural gas, air source heat pump, and ground source heat pump. These costs are based on this winter's electricity price from the Wellesley Municipal Light Plant, from National Grid gas, and from winter costs for oil and propane, and also assuming new and efficient systems for all these heating systems. So the results are dramatic. A baseboard electric heat, again, the most inefficient way to heat your home, and it can cost you as much as $6,000 for the season, as opposed to an air source heat pump, which is a little over $2,000. Again, this is based on actual electric, gas, oil, and propane prices right now. And part of the reason why it's so cost effective in Wellesley is because our electric rates are so low. At 15 or 16 cents per kilowatt hour, we're paying about half of what our neighbors in National Grid territories are paying. So energy costs will vary over the life of your heating system. I was recently reassured by our light plant general manager that he doesn't anticipate electric prices will change in at least the next 3 to 5 years. So we can count on low electric rates. But at the meantime, we are expecting gas prices to increase potentially as much as 500% above current levels by 2050. And the reason for this is, as customers are shifting away from natural gas to heat pumps and other alternatives, the customer base that's supporting all of the pipeline and natural gas distribution costs, the customer base is shrinking, and they still have to bear all the costs of updating and keeping the natural gas system flowing. So that is a good potential reason to shift away from natural gas the next time you have to make a decision about your heating system. And also, I mentioned that heat pumps are produce significantly lower greenhouse gas emissions. This is a comparison of emissions in tons of greenhouse gases that are produced annually per for each heating system. And this is assuming a 3,000 square foot home. And just to put this in perspective, the average per capita greenhouse gas emissions in the United States is about 17 tons. If you switch from fuel oil to air source heat pump, for example, then you're right off the bat eliminating about 9 tons of greenhouse gas emissions just by switching from fuel oil to air source heat pump. So that's potentially over half of your individual greenhouse gas emissions. But because you live in Wellesley and we have a municipal light plant that offers you an alternative called We Care 100%, you can also purchase 100% renewable energy, which would completely eliminate any carbon emissions from a potential heat pump. So that's the end of what I want to present to you. I'm going to turn it over now to Terry Bean and Paxton Halsall, sorry, Paxton, who are our consultants from Abode Energy, which is a partner of the Wellesley Municipal Light Plant, and they provide high-level expert advice at no cost to Wellesley residents who are looking to convert to heat pumps. And if you do call Abode for help, then either Terry or Paxton is the person that you will be talking to. So I'll turn it over to you guys.
Paxton, you want to introduce yourself first?
Yeah, absolutely. So name is Paxton. I am program coordinator for the MLP programs that we have at Abode. So just kind of helping with programs like Lisa said. So if anyone is interested in learning more about, rebates, even consultations that are provided at no cost by Wellesley would be a great place to start. Terry's actually one of the specialists here and offers those consultations. So kind of going over similar things that we're going over in this presentation, but can kind of move into, your specific instance and what you're looking for. So yeah, I'll pass it over to Terry.
Hi, so I'm Terry Bean. I perform consultations for homeowners under the MLP programs. I review some of the quotes that come in. I do some reviews of system sizing and things of that nature, some technical reviews. Kind of a wide array of services offered, and also interact with contractors on a regular basis. So getting to this first slide, what is your existing heat distribution type? It's interesting how often I speak with homeowners who really don't understand what kind of heating system they have. So when we're talking about hydronic heating, we're talking about either forced hot water or steam. So in that case, your hot air is not coming through ductwork, with one exception. I'll talk about that in a little bit. So how you can tell is if you have baseboard heating that is not electric resistance, that would be hydronic. If you have radiators, that would either be steam or forced hot water. You can also tell by your heating system. If you don't see ductwork coming directly out of the system and you see pipes coming out of it, that's a good sign that it's a hydronic system. Sometimes the amount of heating zones that you have, i.e. the number of thermostats you have, indicates one way or the other. Hydronic tends to have more zones. Generally, furnaces, forced hot air have a single zone. If you don't know the difference between a forced hot water boiler or a steam system, a lot of times the system itself will have, for steam, will have like a glass cylinder that's half full of water on the front of it. And that's the way you can tell whether it's steam or hot water going through your distribution. Why this is important is some folks who have hydronic distribution and don't have an additional central AC system don't have existing ductwork that they could take advantage of. So that becomes an additional challenge. So in any case, that's how to identify hydronic systems. And we can talk a little bit in a second about what that means. So now forced hot air systems, and I'm also going to add one little wrinkle with the hydronic delivery here. So there is one type of hydronic system that is referred to as hydro air. And what that means is one of the zones off of the hot water boiler will actually heat up a heat exchanger inside of ductwork, and then that exchanges into hot air. So that could be a case where you actually have a boiler that is distributed through ductwork. Why someone would want to do that is if they added, say, heating to a second floor and AC at the same time, it allows them to do both through the same ductwork. So that's one caveat in terms of hydronic delivery. Otherwise, if you have ducted delivery, it's likely the chance that you have forced hot air, in which case you have a furnace. And so you can see here the furnace that's pictured. This actually happens to be a high efficiency gas furnace. You can tell by the plastic exhaust pipe. But the ductwork coming immediately out of the top of that unit is indicative that it is forced air direct from the unit. Something to know about forced air systems is if they are on ductwork in tandem with cooling systems, there's a substantial chance that the ductwork could be used for heat pump functionality. If it is furnace only, so that it's never accommodated cooling, it's a question, and it's something that you would need to investigate with your HVAC contractor as to whether or not the existing ductwork would be sufficient for heat pump purposes. So we can move on to the next one. Okay, so heat pumps for hydronic distribution. I'm going to clarify this a little bit. So what we're looking at is an air source heat pump. You see that outdoor unit there, which is the compressor, or you can call it the outdoor unit. Either one's fine. That is gathering heat energy from the air. And what we see pictured is an indoor wall unit. Most people know them as a mini split. And this recirculates air from the room. So this particular system I would qualify as an air-to-air system. So the actual delivery of conditioned heating cooling is via air circulation. So it's not taking advantage of a hydronic distribution. However, this is a common solution. If you have, for instance, all hydronic distribution and you don't have any ductwork to take advantage of, this is one way that you could add heat pump functionality if you don't have that ductwork to work with. So more options available for that same non-ducted unit. So when we say non-ducted, what we mean is the refrigerant lines that run from the outdoor unit and carry the conditioned refrigerant are feeding directly into some kind of indoor non-ducted appliance like a wall-mounted mini split. But they also come in other form factors, like as you can see on the right, on the bottom, there's a floor-mounted unit that looks a bit like a modern radiator. Those can be mounted on an interior wall. For instance, if you have a basement available where you could run the refrigerant line set through. So that's one option with that type of unit. There are also ceiling cassettes that you can see picture on the top. They can be, in some cases, slotted into a ceiling between joists, or in some cases, depending on the configuration, they would require some additional framing. They're a little bit more expensive to install because obviously you have to do that additional work. They're limited in terms of how high the ceiling can be, generally 8 feet. And they're also limited in terms of how far they can be from an exterior wall. But sometimes that's a really nice option if folks are focused on aesthetics. I know they're very popular with architects, for instance. So, and this is another interesting distribution unit. Okay, so this is not, I wouldn't consider this a non-ducted unit. This is actually ducted, but it's not the same thing as what we would think of when we're considering like central ducted systems. So if someone has, for instance, central AC in their home, they have a centrally ducted system, which is a fairly substantially sized air handler in their basement or in their attic space, and hard metal trunk that is coming out of that air handler for supply, and hard metal trunk that is going back to that air handler for return, and then some flexible hoses that are coming off of it. That type of system can be retrofit, but it can be expensive. Anytime you're working with sheet metal, it can be fairly expensive to install. This is an alternate type of ducted solution, and it will come under a variety of names. Compact ducted is one of them. Sometimes you'll hear it referred to as small ducted. Sometimes you'll see it referred to as a ducted mini split. Occasionally you'll hear some strange term like pancake air handler, which is what we're looking at there. So this is a smaller air handler than you'll see in a centrally ducted system. And there is no hard metal ductwork that comes out of it. There's just flex hose ductwork that comes out that can treat a variety of areas. It is limited. Basically comes in 2 sizes, one that can treat 2 areas and one that can treat up to 4. And also it's limited in terms of how long of a run the flexible hose can make. But it does offer some advantages relative to the non-ducted solutions in smaller confined spaces where even the smallest wall-mounted mini split might be oversized. So a lot of times a nice line to walk between the advantages of both types is to have maybe a non-ducted unit or 2 in some larger open areas that communicate from area to area, and then maybe in tandem with that, some sort of compact ducted solution for a smaller cluster of rooms that's maybe adjacent to that. So combining those on one outdoor unit is possible. It's called a mixed use system, and those are available. And in this case, this pop-up that just came up in the slide here, what this is referring to is when we're talking about the ability of a heat pump system in cold temperatures, what we're really talking about is its capacity. And that really just means, that translates to how much heat is it delivering. And some systems are designed where they can deliver a similar rate, a similar amount of heating at very cold temperatures outdoors when there is not so much heat energy available in that air. And then there are other heat pumps that cannot do that, or they're not designed to do that, is maybe a better way to say it. So they won't stop working in colder temperatures. but the amount of heating that they supply would be reduced. So they might not be suitable for full-time heating. So why would someone want one versus the other? Well, if you have a very old, very inefficient heating system that's maybe nearing end of life, you might want to be considering complete replacement, in which case you'd want a heat pump that was designed to supply a consistent rate of heating regardless of the air temperatures outdoors. But if you had, say, a very high efficiency gas system that was maybe only a couple of years old, and you really weren't interested in parting with it fully, you could add heat pump functionality onto it that would provide your full cooling, but also still cover a portion of your heating load. And even if you, say, selected a system that was only maintaining its full capacity down to something like, let's say, 25 degrees, for instance, if you imagine our heating load throughout the heating season, most of our heating days are actually above 25 degrees most of the time. So even if you're adding a heat pump functionality onto high efficiency combustion fuel, then you still are increasing the overall efficiency, reducing the overall carbon footprint, and maybe getting the best of both worlds. And in the future, you could still replace both of them at some point in the future with a full-time heat pump. So both options are available. Okay, now this is an interesting additional type of distribution. So what we were talking about in previous slides were air-to-air systems. So the non-ducted and ducted units would be delivering both heating and cooling via air, either recirculated in the room or directed out through ductwork. This is actually a system that can use your existing hydronic heating potentially to supply heating. These systems are a bit more complicated. So they're not nearly as popular as air-to-air systems, and largely because the air-to-water systems that were previously available could only get the water temperature to a level that wasn't as high as what, say, a gas boiler would get it to. So what that meant was, in order to supply the amount of BTUs that you would need to maintain temperature, you need a larger area. So a lot of times these types of systems were relegated to folks that had, say, radiant floor heating that had a lot of area, or in some occasions, possibly even radiators. So those were limited cases. And even in those cases, that worked great for heating. But when you think about the cooling aspect of the heat pump, one of the things cooling does is it creates condensate. So you have to think about, how are you going to deal with the condensate generated by cooling? And if you're using some kind of hydronic distribution, dealing with that condensate becomes quite a challenge. So typically, there would be some sort of additional ducted cooling solution working in tandem with the hydronic heating solution, and that's still the case. What's changed recently with some of these systems is that water temperature with some of the newer systems can get high enough where they don't need necessarily radiant floor heating or radiators. They can actually work with baseboard. We saw one recently in Melrose that was able to do that. So what the system in Melrose looked like was, he was able to use his baseboard hydronic distribution for the heating aspect of a air-to-water system, but he still needed a high velocity 2-inch flexible ductwork system to handle the cooling aspect, so that you could also handle the condensate, and that also amended some of the heating supply. So it can be a little bit more of a complicated situation if you want to keep your hydronic distribution as part of the heat pump heating. It's possible. Just be aware that you would want to work with folks who are quite experienced with this type of system, and that it's a bit more complicated to install. There are some companies that are specializing a little bit these days, and if somebody's really interested in this type of system, we maybe have a contractor or two we could point you to. One of the additional advantages of that system, just before we go off at one final time, it does offer a domestic hot water solution as well. So you notice in that top slide there, you're seeing a tank that's sort of midway through that distribution. And similar to the way an indirect water tank would work with a hydronic boiler, that can also be part of a hydronic heat pump solution. That's not part of the air-to-air or ground-to-air systems. So that's an additional benefit of hydronic. But again, something that you'd want an expert to design for certain. Okay, so if you have the advantage of forced air distribution, it could be as simple as if you have, cooling already on that system, what that indicates is the ductwork is sufficient to handle the cooler air, which has it's more dense air than hot air. So it has a harder time moving around ductwork. So if ductwork is already accommodating cooling, there's a pretty substantial chance that it will accommodate both the cooling and heating of a heat pump. If your ductwork has only accommodated heating and never cooling, that's an open question, as I mentioned earlier, and something that your contractor would need to assess. If you need extensive ductwork to accommodate a heat pump, that can add some significant costs, and that's when you may consider possibly a non-ducted solution as an alternative. But if you can use your ductwork, it could be as simple as swapping out an AC condenser with a heat pump compressor, swapping out the air handler, and putting in a new line set. And that could be as simple as it gets for the installation, which could be fairly cost effective. So to the right, we have ground source heat pumps. These can use forced hot air distribution, but they can also use hydronic distribution as well, potentially. One advantage of a ground source system, and we noticed in the chart earlier that we were looking at in terms of the operating costs, the ground source systems came out on top. The reason for that is that they are working with fairly consistent temperatures under the ground, right? It's a few feet below the surface of the earth. It's always about 50 degrees, a little cooler than that in the springtime, a little warmer than that at the beginning of the fall. But in general, they're always working with about 50 degrees versus air source systems that have to work with more variable temperatures and in some cases significantly colder temperatures that have a lower heat density. So they have to work a little bit harder. So that tends to make ground systems operate more efficiently, albeit the initial cost of installation can be substantially higher than an air source system. So in most instances, what we see is folks are going with air source systems, cheaper to install, faster to install. There are occasions when ground source systems make sense. If somebody's a new homeowner, they got plenty of property, they're planning on being there for a while, they could recoup the additional cost of a ground source system over time with the increased efficiency of that system. So as we mentioned earlier, the existing ductwork's got to be suitable. Hopefully it's insulated, well sealed, and sizing is important. And this is where ductwork can get a little bit tricky. You have to have a certain amount of air that's delivered in order to deliver the BTUs that you need, either of heating or cooling. But if that air amount delivered in the space requires an airflow, that means that the air has to travel across the coil that conditions it too quickly, then the coil really doesn't get a chance to get the air up to temperature for heating or chilled sufficiently. So it's this balance with ductwork between the speed of airflow over that coil that's conditioning it and the amount that is needed to be delivered to deliver the BTUs needed for that space. So you really need a licensed contractor with experience in ductwork to let you know whether or not that ductwork is sufficient. There are tests that can be performed on ductwork to tell you whether or not the flow rate is sufficient. But in general, ducts that are sealed and insulated well are going to perform better than ones that aren't. All right, so ground source versus air source. We talked a little bit about this. In terms of the ground source, yeah, we have higher efficiencies available, as we talked about, because it has more heat energy available year round, right? Heat energy available in wintertime and 50 degrees for cooling is pretty easy to use in the summertime as well. That's a good point about aesthetics, nothing above the ground. And this actually is surprisingly common question. Folks ask me how loud an air source compressor is. That can vary. There are some data points available for the actual decibel output of an air source system, but certainly ground source can avoid that. Some of the things that you want to consider with ground source systems is you're looking at either drilling or digging. That can be fairly invasive. It can be a little bit cost variable. If you drill a well for a ground source system and the well collapses, you're still on the hook for the cost of that, and you've got to drill another one or more. So that's just something to keep in mind. But in the long run, they are going to operate more efficiently. Air source, lower first costs, no disturbance of landscape. It does require a smaller space, certainly. So for more urban type areas, it's a better solution in many cases. And yeah, the ductless options that are currently available gives a lot of flexibility. So that's what we still see as the largest portion of the market in Massachusetts. Okay, and actually, this has been kind of coming up a fair amount recently. In fact, I think I just spoke with a Wellesley resident about heat pump water heaters a couple days ago. So if you think of the technology of capturing heat energy from air and then using that to heat the air inside of our homes, imagine the same technology that is capturing heat energy from air, but using that to heat water inside of a tank. So it's leveraging that same advantage of existing heat energy, thermal energy that is available in the air. So when you're looking at these photos of heat pump water heaters, that the first one there on the left is the easiest one to sort of delineate. The top unit there, that black section, is essentially akin to the outdoor compressor for the type of air source heat pump that you would be heating your home with. It would be, in this case, capturing heat energy from inside and delivering that heat energy into the water. So it is going to be multiple times more efficient than, say, your standard electric resistance water tank, which is essentially a sort of a giant tea kettle. Many of these systems, if not most of them these days, come as what they call hybrid systems, which means that they will revert to being a standard electric resistance hot water heater if there is a technical failure of that compressor on the top, which is nice. That means that if there's an issue, you'll still have hot water until you can get that compressor serviced. What's important to know is that this compressor that's on top of the unit would be drawing heat energy from a basement area. So they really aren't suited to being tucked into small, confined spaces like utility rooms. If you need to put them into an area like that, then you'd want to make sure that they have as much passive ventilation that affords them access to the larger volume of air in the basement as possible. That's really important. The more volume of air they have available, the more efficiently they operate. They will also tend to cool down the temperature in your basement by a couple of degrees. So in most cases, that's not an issue. A side benefit of that is in the summertime, they tend to dehumidify. So if you're using a dehumidifier currently, you may not need to, or you may need to less if you have a heat pump hot water heater. They are becoming on the marketplace, becoming available in the marketplace, some newer heat pump systems where that top compressor unit is actually split off of the system and it's outdoors. There's some increases in efficiency for those types of systems because the compressor is bigger, but the price of those systems is right now pretty high. It's at least several $1,000s for those systems. So they represent a fairly small portion of the market. Right now, these types of systems are probably around $1,800 off the shelf plus installation costs. So you're probably looking at about maybe $2,200–2,500 installed. They also come with some models becoming more available in New England that actually are 120-volt plug-in. So you don't have to have the hard wiring done from the main panel. If you have an outlet available that you can take advantage of in the basement, potentially you could plug in one if it's a 120-volt model. You'd still need to get the plumbing hookup, but that would save, one professional that you'd need to deal with. So,
Eric, I'm gonna, before you get too deeply into this, to give us enough time to talk about costs and stepping forward with the plan, I'm gonna turn it over to Mary to talk about costs, and any more detailed questions people have, we can wait for the Q&A to answer those. Thank you so much for all that really helpful information.
you're welcome.
And next up is Mary Gard, who's going to talk to us about the costs associated with heat pumps.
Hi, yes, my name's Mary Gard. I'm a member of Sustainable Wellesley and the Climate Action Committee, and I'm a Wellesley Energy Coach, which we'll talk about later. So we already talked about the operating costs of heat pumps compared to fossil fuel appliances. And I'm here to talk about installation costs and mostly about the incentives available right now for electrification and efficiency. So there's now a list of all available electrification incentives posted on the Climate Action Committee's website with links to their sources. So we have federal, state, and local. We'll be updating this list as incentives change. This slide is a picture of just one page of all these incentives. There are 8 pages total for everything from heat pumps and appliances and insulation to electric vehicles, yard equipment, solar panels. But today we're talking mostly about heat pumps, but we do encourage you to explore the other electrification and weatherization incentives available to you. Next slide. So breaking down these incentives, there are 3 types available to Wellesley homeowners, and they can be added together for maximum impact. We have the utility rebates, we have the loan programs, and we have federal tax credits. So first of all, utility rebates, it depends on how you heat your home, your current fuel. So if you're a gas customer, you go to Mass Save for your rebates, and that's National Grid. And they're probably, these utility rebates are probably the biggest incentives for heat pumps right now. You can see that if you convert your home's heating entirely from gas to air source heat pumps, you get a $10,000 rebate from Mass Save. And this is the agency that handles rebates for National Grid, your gas company. A hybrid system that Terry was talking about, where you use gas as a supplement or a backup to your heat pumps, allows a smaller but still significant rebate of $1,250 per ton from Mass Save. Converting from gas to a ground source heat pump gives you an even bigger rebate of $15,000. And then also, if you convert to a gas water heater to a heat pump water heater, Mass Save will give you $750. Now, if you're converting from oil, propane, or electric resistance, then you turn to the Wellesley Municipal Light Plant, your electric company, for rebates. Their heat pump rebate is even more generous per ton, but they have no bonus for a whole home conversion, where you turn off your fossil fuel completely, like Mass Save does. The MLP's rebate for converting your water heater to a heat pump water heater is $500. Altogether, you can get up to $10,000 for converting your home heating to air source heat pumps, no matter how you currently heat your home, except for homes that are currently heated with electric resistance, and they're not very many of those. And in that case, the maximum heat pump rebate is $5,000. Next slide. So that's the first incentive, the utility rebates. The next one is the financing. If you heat with gas, Mass Save, again, also provides a 0 interest loan for 7 years. So you'll get $25,000 for help with weatherization, that is insulation, air sealing, new windows and doors, etc. And they can loan out up to $50,000 for a heat pump installation. If you heat with oil, propane, or electric resistance, there's currently no such utility loan program like the Mass Save heat loan, but there are plans brewing at the state level to roll out a new 0 interest loan program to include more homeowners than just gas customers, using money from the Inflation Reduction Act. So stay tuned and we'll let you know when that rolls out. So the third incentive is the federal tax credits. So I didn't talk much about the rebates, the utility rebates for energy efficiency, but there are a lot that the utility companies provide, like almost free insulation and help with windows and doors. So the federal tax credits, the first one we're talking about is about the same thing, weatherization. So you get all this various incentives for home efficiency improvement measures. And you can take them up to the annual caps shown here. And then you can combine these credits each year up to an annual combined cap of $1,200. So what you can do is plan ahead and take advantage of these credits, adding insulation this year, replacing a few doors next year, maybe a few windows the year after that. The electric panel board upgrade on this page, by the way, is only for panel upgrades related to efficiency installations like heat pumps. So this energy efficient home improvement credit runs for 10 years. So we have 9 years left. So every year you can take this $1,200 annual cap. Okay, so the next one is the same section of the Internal Revenue Code. It's part 2, and this is the same thing. You get 30% tax credit, and it's for air source heat pumps and heat pump water heaters. So again, you can gradually improve your home's efficiency over the next 9 years by taking advantage of this tax credit every year. The overall annual tax credit, like I said, is $3,200 because you can combine the weatherization tax credit from the previous slide, which is $1,200, and then this $2,000 heat pump credit on this slide. So you combine it and you can actually take $3,200 tax credit every year for the next 9 years. So the next tax credit is under 25D, and this is more about renewable energy. But in this tax credit, that's where they deal with the ground source heat pumps. So it's the same deal. It's 30% of your costs, including labor, of installing a ground source heat pump, solar, or batteries, even if the batteries are not connected to a renewable energy source. You can take 30% of those costs and apply it against your income tax. This time, there's no annual cap. So it's up to you. You can take this credit each year for the next 9 years. There's no annual cap, so it's really a significant tax credit if you want to pursue renewable energy for your home. I would like to point out that all these incentives, the utility rebates, the loan, the federal tax credits, have a fair amount of qualifiers, such as certain efficiency criteria for window replacements, or you have to have certified installers for your heat pumps and installation. So these criteria are not difficult to meet, and your installer should already be aware of them, but the regulations do change. So be sure to consult your installer or your energy coach and or a tax advisor to stay on top of them.
Treating leaves me red, flaky, irritated. CeraVe Acne Cleanser.
I'm not sure whose speaker that is, but so now we're going to turn to some examples of how you can stack these 3 types of incentives to save money while improving your home's efficiency. So we're looking first at
Isaac, and I have been married for 5 years.
Can someone turn off their
and we both like each other's company in different ways.
Dennis Cerati, thank you. I think that was coming.
Okay, great, thanks.
I think I found it.
So let's turn to some examples about how you can stack these 3 types of incentives. I'm looking at a home now with, let's say it has an aging gas furnace. So like Terry was explaining, it blows warm air through the house. This home may or may not have existing air conditioning using these same ducts. But let's say that this AC either needs to be replaced or installed as new in the next few years using the same ducts. So I will assume in all of these examples, that the home's weatherization has been updated after a thorough energy audit, all of which has been substantially paid for either by Mass Save or the MLP. I just want to point that out, that I'm skipping a step because we don't have time. But so you start with the weatherization, but now the homeowner has the choice of either putting in more fossil fuel systems and a new central AC, or on the left, putting in a heat pump system, which both heats and cools the home using the same ducts. So the owner decides on the right to stick with his current fossil fuel gas system and replace his aging equipment with standard new equipment. Starting in August of 2024, Mass Save will discontinue any rebates for all fossil fuel equipment. There is a small $600 federal tax credit for the very highest efficiency gas furnaces, but they cost several $1,000s or more, up to $12,000. So this owner is choosing the standard furnace. This is the $7,000 median price in Massachusetts this year for a regular gas furnace. And so he's going to forego that $600 tax credit. So at first glance, the initial cost of the heat pump system in the left column looks high in comparison, but you can see that the incentives quickly bring that price down. First, the Mass Save utility rebate of $10,000, and then the federal tax credit of $2,000. I should point out that the 30% tax credit, which is calculated after all the utility rebates, should be $4,200, but the annual cap under this section of the code, as I mentioned, is limited to $2,000. And then finally, there's the Mass Save heat loan of 0% interest for 7 years. The homeowner who converts to heat pumps can take advantage of this offer, but starting in April of this year, Mass Save heat loans no longer are available for installations of fossil fuel equipment. And that's why you see the difference between the two bottom lines on this page. Now, if you're an oil, propane, or electric resistance customer, you can't take advantage of the Mass Save heat loan. But as I said, there is a program coming down the line, not too distant future, that will have the same setup, hopefully. Okay, and then my last example is looking at a different home. And the only difference is, like Terry said, there's radiant heat, or I'm sorry, hydronic heat, and then there's furnaces. And so this is the hydronic heat home. So there's radiators or baseboards or radiant heat. There's no ductwork in this house. So in this case, there's no air conditioning. Let's say there might be some window air conditioning, but the owner doesn't have anything set up. So installing ductwork is expensive, especially in older homes. So although the standard gas boiler for home heating here is relatively inexpensive in this example, in the right column, the air conditioning is not. Installing ductwork costs between $3 to $7 per square foot of a home. And again, there are no Mass Save utility rebates for either the fossil fuel boiler or the central AC, unless the AC is high efficiency enough to qualify for the federal tax credit. And that's only a $600 tax credit, and it's a very expensive system. So assuming the less expensive gas boiler is not meeting the absolute highest efficiency rating, there's no $600 federal tax credit for that boiler, but there might be one for that air conditioning if it qualifies. So the price of installation on the left column for a ductless heat pump system varies widely. I've listed the median price with 4.5 zones. That means, the different heads in a ductless system. But the price depends on the configuration of your rooms, the size of your house, how many heads you put up. Plus, the price goes higher, as Terry mentioned, if you choose ceiling and floor units instead of the standard mini split head on the wall. So I'm just choosing the current median price for a ductless system. Again, you get the utility rebate for $10,000 for the heat pump, and you get the federal tax credit of $2,000. Plus, since he's converting from gas, he gets the Mass Save heat loan with 0% interest. So clearly, again, the heat pump system is the better long-term choice. So that's about it. In summary, I just would like to point out that you have to look at this installation cost difference and remember that you're eventually going to have to look at heating and cooling equipment, and it's cheaper to install and maintain one system compared to two. Also, don't forget the incentives. They're out there. I don't know how long they'll be out there. So you should take advantage of them while they are out there. Also include the reduced operating costs that Lisa mentioned. And remember that fossil fuel costs are likely to increase faster than electrical costs. And there's something we didn't discuss, but there is an increase in home resale value when you electrify. So I think that's about it. There's other intangibles to consider: the health benefits, the comfort benefits, improved resale of your home, and of course the greenhouse gas benefit. So next we have, I think Lisa is going to wrap things up, or Mary Beth, I'm not sure who's coming up next. Thank you.
I'll talk about this. Thanks so much, Mary. Yeah, there are a lot of compelling reasons to consider a heat pump, but it is a somewhat complicated process depending on where you're starting. So it's good to have an action plan and to get help and resources along the way. So first of all, if you are considering a heat pump, these are the circumstances that you might be thinking about getting a heat pump. First, your heating system or your AC system is over 15 years old, i.e. at the end of its life, and ready to be replaced. Then consider a heat pump, because you can replace both your heating and or your cooling system with a heat pump. Also, water heater, if it's over 7 to 10 years old, it's also prime for replacement, and the heat pump, again, can serve your purposes. The next reason that you might want to consider a heat pump is if you're adding AC to a home that doesn't already have it. And again, you should consider the benefit of heating as long as you're installing a new cooling system as well. And last, although it's not required currently that any new construction use a heat pump or non-fossil system, it is both economically and in terms of carbon reduction, it is the best choice. So if you're planning a renovation or an addition or new construction of any sort, then please consider a heat pump to meet all of your heating and cooling needs. And plan ahead. If your fossil system is dying and it's the middle of winter, you will not have time to think about and plan for installing a heat pump. It takes several months at least to go through the process of a design and comparing costs and figuring out what is best for your home. So it's a good idea to start planning now, or as you're approaching the end of life of your heating or cooling system. So the process for getting started is whether you're starting from scratch or not. Wellesley now offers a new Energy Coach program, which has been offered since November of last year. Energy coaches are volunteers trained in clean energy technologies who can help residents meet their energy efficiency and decarbonization goals. They can also provide information about local, state, and federal incentives. And although this is optional, it is a great place to start if you have any questions at all about the process for decarbonizing your home. But regardless of where you are, the first step, whether or not you need an energy coach, is to get a no-cost home energy assessment. And that who you will go to depends on how you heat your home. If you're a gas customer, you will go to National Grid to get your energy assessment, or non-gas customers, propane, fuel oil, or baseboard heat will go to the MLP partner, the Center for Ecotechnology. And the numbers are here for who you will contact. These slides will also be distributed to everyone on this call, so you can refer to these numbers for help. So the energy assessment will recommend ways to maximize your home's insulation and air sealing so that you're minimizing the heat loss through the walls and doors and windows. So whether or not you're upgrading to a heat pump system, we highly recommend that you get a no-cost audit and follow all the recommendations so that you're not throwing money away because of a leaky home situation. And meanwhile, while you are going through the weatherization process, that's a good time to be contacting installers to consider what kind of heating system is appropriate for your home, depending again on what your fuel source is now. And Abode offers a list of preferred contractors, so you can narrow down the list substantially and choose contractors who have already been working in Wellesley and are trusted. And from the installers, we recommend that you get several quotes because each quote will be different and they can vary wildly in terms of costs and even design recommendations. There is never a single right way to install a heat pump. There are a lot of different possibilities. So it's good to get several quotes and several design options. And then the last step of the process is to go back to Abode with your quotes and your designs, and they will do a very thorough design review and help decide what is the best and most appropriate system for your home. And they also have a cost comparison tool or a quote comparison tool, which can help you decide what the best value is for the installations that are being recommended. So in summary, there are a lot of compelling reasons to get a heat pump, from lower operating costs, lowering your carbon footprint, improving your indoor air quality, and increasing year-round comfort. So we hope that all of you who are on this call are considering making the switch, and we'll open it up now for Q&A. Thank you all for listening, and we hope that you have some questions for our Abode contacts.
Thank you, Lisa. Thanks very much to all the speakers. And I want to thank a couple of our audience members, Catherine Ruffin and Tom Atkinson, for giving some testimonials in the chat. They had worked with Terry Bean and had great things to say about that experience. So yeah, we'd love to take questions. If you could raise your hand on Zoom. I'm actually not seeing. Oh, yes. Okay, Meg, would you like to ask the question? Meg Davis, would you like to unmute yourself to ask a question?
There we go. Is that better?
Yeah, that's great.
Great. Thank you. So my question refers to noise. I feel like although you had a very complete presentation, the noise level piece was skimmed over. And I'm concerned about making that kind of investment and then having a really loud noise outside or inside. Can you address the noise level?
Sure. Would Abode like to take that?
Yeah, I can talk a little bit to that. So in terms of the indoor equipment, you really shouldn't experience noise at all. Most of the working mechanism of a heat pump, especially an air source heat pump, is the outside unit. So that can potentially generate some noise because you have fans and a compressor. In general, it shouldn't be an egregiously loud system. A lot of folks are familiar with really old central AC systems that haven't been well maintained and are frankly probably past their useful life, making a lot of noise. Heat pumps in general shouldn't do that. That said, there are decibel ratings for each system. I'd like to tell you that there's some location where they accumulate that data and you can compare one to the next easily there's none that I'm aware of. There is for each heat pump essentially a data sheet. In the case of a heat pump, they refer to it as a submittal, and the submittals oftentimes will have the decibels of output. So that information is available, and you could ask your installer for it.
Thanks, Terry.
Sorry, I just wanted to ask a quick follow-up question and then turn it back to you if you had a follow-up yourself. But some of the noise, I think, can be caused by a vibration of the heat pump if it's not properly attached to the house, or can transmit that vibration to the house. Can you talk about that?
Yeah. So in many cases, heat pumps are mounted on ground mount elevated platforms. If someone opts to mount it to the home, then there is always the case of vibration being carried through the home. So I would say one way to avoid noise issues is to avoid mounting it to your house if you don't have to. And that can be avoided. There are some measures that can be done to sort of act as shock absorbers, but in general, if you can position the outdoor compressor away from a window and mount it on a ground platform versus a wall-mounted, rack system, you'd probably be better off in terms of mitigating any kind of noise.
Thank you.
Fred, did you want to speak to this?
Yeah, I just wanted to maybe ask the people that have put in a heat pump, comment on it versus the old AC unit that they may have had.
Well, I'm happy to weigh in. I'm a consumer and I'm happy with my new system. Terry Bean helped us get started about a year ago, but the work was done over the summer. And it is, we have a heat pump system that is located outside our house, and it's on a concrete little platform. And I can't hear a thing. And I tested with my neighbors. I said, is this bothering you? And they said, what's bothering us? I have to walk outside my house and like lean into the unit to see if it's, I know it's working because I see the fans, but I don't hear a thing.
Any other heat pump owner that would like to weigh in on that? I have heat pumps in my home as well, and they're very quiet. And when we did research into this a few years ago, I think that it was what I remember is that the heat pumps are considerably quieter than conventional air conditioning condensers. But thank you for that question. Danny, did you have a question?
Yes, thank you for the presentation. For someone who is, knows absolutely nothing about the inner workings of a house, can you briefly summarize the importance and relevance of existing ductwork when installing a heat pump?
Sure, I can talk to that. So you can break down the indoor distribution options for heat pumps into two general categories: non-ducted units and ducted units. So non-ducted units have refrigerant flowing directly into an appliance that recirculates air from the room, and we saw several configurations of those earlier on one of the earlier slides. Ductwork would use a central system like an air handler, where the coil that conditions the air is in that air handler versus in, say, a wall mount unit, and the air passes across that coil and is then distributed out via ductwork. There are advantages and disadvantages to each type. Non-ducted systems tend to be lower cost to install. They tend to be highly efficient, but the technology limits how small they can get. And I don't mean by physical size, it's how many BTUs per hour they deliver. So in some cases, non-ducted units can be a challenge if you're trying to treat multiple small spaces that are walled off and have a door. That's where the advantage shifts to ductwork. So if you have existing ductwork, a lot of times it's an easier way to just accommodate the variety of spaces that you have, but it's not always suitable, right? So if it's not suitable and you have to amend your ductwork, that can potentially, depending on what the amendment looks like, add significant cost to your overall system. So you're always walking this line between the efficiency of non-ducted, the sizing advantages of ducted equipment, whether the ductwork will be suitable. It's going to be different with every particular scenario. I know that's not a clean answer for you, but I hope that fleshes that out a little bit more.
For that, thank you for that. So it obviously depends on the layout of the house.
Yeah,
If you don't have any existing ductwork, do you need to install wall units to transfer heat and
Could be-
cooling?
yeah, could be wall
Whatever.
units, could be floor units, could be ceiling cassettes. They come in a variety of form factors, the non-ducted equipment, and are best suited for larger areas that are sort of open and communicating. If you have smaller areas like small bedrooms, small dens, offices, etc., that's where the ducted systems can shine. So sometimes a combination of the two is the best bet, but it really depends on what your particular circumstances are.
Okay, so this is the additional cost that Mary was referring to in her cost breakdown, is the assumed cost of adding more, additional units to distribute the heating and cooling.
Yeah, that can be. And that's also, by the way, a little bit of a red flag. So if you have, Mary was mentioning, that's really dependent sometimes on like the number of indoor units. And it's not just about the initial cost, but it's also potentially about the performance. So if you have, say, I don't know, 6 rooms and 4 of them are rather small, and a contractor comes in and says, that's not a problem, we'll put an outdoor unit and 6 wall mounted units in here, that could potentially have performance issues in the rooms where those units are small. Whereas a better solution might be a lesser amount of total units, and folks are willing to leave their doors largely open throughout the day. We actually have a co-worker here who does that, 5 rooms in his second floor, heated by 2 wall mounted units, heated and cooled. And his house is very well insulated. So he leaves interior doors open during the day, and it covers all of it with just 2 units, which is obviously kept his initial cost lower, but also it was more appropriately sized and operates with more efficiency. So his operating cost is lower as well. So this is where as Lisa was saying, there's lots of complications that can work into his design, and this is where it's worthwhile to take your time and plan ahead and have these kinds of conversations, both the contractors and heat pump coaches, and potentially with the boat if you need to.
Right.
Yep.
Thank you. For what it's worth, we had no ducts in our house, and we have a split system. So some rooms have the wall mounted units, and I have 5 rooms on a ducted system out of the attic. So there's lots of options. Christopher?
Yeah, thank you. This has been great. It's we've got a 16-year-old house, so with all original heating and AC, so we're getting to the end of our useful lives. We have an unusual situation. We have oil heat with a boiler and 2 air handling systems, one in the attic, one in the basement, and the AC runs through that ductwork as well. How do we assess whether or not that's going to be sufficient for heat pumps, or whether we're going to need to go to ductless or all that? How do we go about it, guessing, learning about that?
Ultimately, your HVAC contractor is going to need to determine that, but how many condensers do you have for your cooling system?
2. One
So
for each
perfect.
air
That gives you an
handler.
opportunity potentially to have 2 separate heat pump systems, which gives you the opportunity to operate them independently. You could operate one at a time. You could operate them at 2 separate consistent temperatures. There's some advantages to having more than one. In general, if the ductwork has accommodated cooling, it's probably going to be okay, because cooler air is denser air, harder to move around ductwork.
Yep.
So it can accommodate the cooling aspect of the heat pump, and the heating aspect shouldn't be an issue. But in the end, you really do need to have HVAC eyes on it, and they need to make the final decision for you.
Okay, great.
Or
Thank
help you with the final decision. Let's put it that way. Yeah.
Okay, great. Thanks. Appreciate that.
Phyllis?
Thank you for a great presentation. So I have exactly the same situation that Christopher does. However, my house is 100 years old. I had read that the compressors condenser, it can only be so far away from the source. Is that an issue with the heat pump installation?
Not sure what you mean far away from the source. The compressor is the outdoor unit
Right.
and the air handler would be the indoor unit. But in terms of, I think what you're driving at is the length of refrigerant
Yeah.
line running from the outdoor to the indoor unit. Yeah, there are some limitations. And if that run is excessive, it can actually lose some of the heating and cooling conditioning of the refrigerant over the length of that run. So sometimes that can be overcome by sizing up the outdoor unit a little bit to accommodate for that. That's another good question to ask HVAC when they're on site. How do we work around this? Is this going to be a concern?
Great. Thank you very much. I appreciate it. Great presentation.
Any other questions? Or Lisa, did you want to end with anything?
Well, I am really grateful to have such a large audience interested in heat pumps. It's really encouraging and warms my heart personally. It is part of my mission working for the light plant to get people to convert away from fossil fuel systems. And there are a lot of reasons besides just reducing your carbon footprint, as we've gone through, health and cost savings and comfort. So I encourage you all to, first of all, reach out to the Energy Coach program if you need help getting started, and reach out to the Municipal Light Plant if you have any other questions about your electric supply or conversions. But don't forget, once you get started in the process, that Abode is a valuable resource when you get to the endpoint and need help evaluating designs and comparing costs of any system that you have a quote for.
Phyllis, did you have a question? I saw your hand go up.
No, just saying thank you.
Okay. Okay. Thanks, everybody. Thanks to our speakers. Thanks for everyone for coming and for your great questions.